working harder on the one best. So anyway, so let's get started. Hopefully you all got to download the handouts or the notes. And yeah, so just heads up, the first and second chapter is kind of boring. It happens. There's a lot of blah, 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 lots of definitions. The maths and the fun part gets going by chapter 3. So just deal with me, and bear with it, and just be patient. And hopefully eventually we'll get to the fun part once you get here. Okay? So we start with chapter 1, which is basically about fluid properties. As you can imagine, there's going to be lots of definitions about what's a fluid, what behaves, this sort of stuff. So just a quick question, is this size about right for the folks down there? Did you get to see something? I guess the lack of answer is a yes. I like to be positive, so unless you change to a no, I'll assume it's a yes. So any guess about what a fluid is? We have some volunteers that would adventure on defining a fluid. Sorry? Yeah, it takes shape, it adjusts the shape to the container. That's a nice way to see it. Another way, it's kind of funny, right? It's something that you guys live in, you see it on a daily basis, but we have a hard time describing it.
Molecules attached by non-bonding forces?
Well, that wouldn't make your chemistry professors very happy, because any sort of molecules do have some sort of bonding forces. Though the thing is, when you get your glass full of water, do you get to see any molecules? No, right? I mean, at least my eyesight is bad enough that it doesn't get to see it.
A gas or a liquid?
It can be a gas or it can be a liquid. But I also show you a glacier on my first lecture. And a glacier can eventually also be considered as a fluid. And so there was another hand somewhere there.
It's a pretty medium that interacts with that has kinetic properties.
Yeah, that's a neat way of saying.
Always gets into shear stress.
Exactly. There you go. That's kind of a key point. It's a substance that doesn't hold any sort of shear stress. Okay, what do we mean by shear? It means any sort of force. You know, if you touch it, it will deform. Okay, so this is the big difference between a solid and a fluid. A fluid, if you push it a little bit, it will deform a little bit. If you keep pushing it more, it will deform more. And it will keep deforming. It adjusts to the container we saw earlier. While if you compare it to a solid, you might deform it a little bit, and eventually you will crack it or you will break it or something. But a fluid keeps deformed under shear. So if we just write the proper definition, for the sake of the beauty of your notes, we could say a fluid is a substance that deforms continuously under the application of a shear stress. Okay, that's the key way of talking about a fluid. Alright, so that being said, now we know each time I'll be talking about a fluid, you understand what I'm talking about. Now, as I said, I made a comment on my introductory lecture relating to the units. Okay? And so, to actually talk and describe and quantify fluid properties, we need to agree on a unit system. Okay? So we have what we call a system of units. Yeah. So we have 3 different systems of units that are kind of used. Luckily, we have, I would call it the most important one, which is the international system, where we all agree in a common ground. Okay? So in this one, it's called NLT, capital T, and we'll quickly see why. So it's basically characterized by where the main variables are mass, length, time, and temperature. Okay? So we have mass. Length, time, and temperature. Now, how do we measure mass in the international system? Kilograms, pretty easy. Length, all right. Time, right. And temperature. Aha. Kelvin. All right. Then we have a second one. This is super cool. I can keep writing without erasing. So we have a second system, which is basically the British gravitational. Okay, so in this one, we'll have force, length, time, and temperature. Now, how do we measure force here?
Pounds.
Pounds, okay. Length. Alright. Time. Okay. And temperature.
19.
Like that. Okay. Excellent. And then we still have another one. In case we didn't have it now, we have what we call the English engineering. Okay, so this one is more interesting because, yeah, they certainly weren't thinking about making things simple, just trying to make it as complicated as possible. So they decided to use force, also mass, length, time, and temperature. So again, what are the units for force? Mass, pound, length, time, and temperature.
Fahrenheit.
Fahrenheit. No, we keep the same Fahrenheit. Okay, but does anybody realize of a major issue here? Come on, let's answer Jesse. Any idea? Wild guesses? Yeah, what happens with that? Yeah, they are different units. We still call them pounds. We make a different force and mass. It's just that the English were not very original, but still okay. Two different names, although they share the pound. What else?
Mass in the British gravitational.
Yeah?
Not accounted for.
It's not accounted for, but it's not accounted for either. What's the difference between British and international system? Think about your physics class 101. We have a problem, right? Although you're still not aware of it, we have a big issue here. In this one, we don't have force. Alright? But in this one, we don't have mass. And in this one, they missed both, so they thought, oh, let's put both in. Okay? So here we have a problem. Have you ever heard about something in maths called overdetermination? Right? What's the most important, what are the laws of Newton? Okay, so we have, how many of those laws do we have? 3, alright, we're good. So, the second one is basically, I would say, the one that rules everything, and it's certainly going to rule fluid mechanics. So if you remember Newton's second law, there's something like sum of forces is equal to the mass times the acceleration of a object. Now, in the Earth we have, well, sometimes we have here, when we're looking, for example, at the vertical displacement, we have the gravity, right? Now the problem is, imagine in the case that we're just interested in the vertical direction, we would have force that would already be defined here, we would have mass, and we would also have gravity that would be determined. So then we could find a combination where this equation wouldn't hold. Very nice. Okay, so just said in another way, so if I'm looking just at the vertical direction, we put it this way, we know that in the vertical direction the acceleration is due to gravity, right? You're already lost, or? Alright. So, if now I come and say, well, I can define my force and mass through my system of units, this is defined. This is also defined, but it happens that my G is also defined. Then I have a problem, right? Because there might be situations where this thing doesn't actually satisfy this equation. Okay? So to make this system work, they had to come up with a new combination, and they had to actually rewrite Newton's second law. So they had to say, well, now we will write Newton's second law as a force, mass, and acceleration, and we will divide it by a correction function, or a correction constant, GC. Okay, so if you want, they correct it for the gravity. And this GC was defined as 32.2 mass pound divided by force pound second squared. Alright, this is just a constant proportionality that was defined such to keep satisfying Newton's second law. Okay. Alright. So this is really important. Keep this in mind, because in my exams I love playing with units. Okay, so I don't like numbers, keep that in mind, and I love units. Okay, so normally in my exams I give you as a present 1 point for units. Normally students fail this point. So most of my exams nobody gets it. Okay, just because they overstate when they study, they don't pay attention to units or dimensions of the variables. Okay? I'm already saying to you, and I know in the midterm, half of you will not get that question because you will have thought, oh, he was just bullshitting us. Okay? So no, if I say something goes to the exam, goes to the exam. So take advantage of those things. Okay? All right. Let's keep moving forward. So now we know what's a fluid, we know what to measure, but one of your colleagues pointed out a problem. It's like, sure, fluid is made of molecules, right? So now one of you could ask, like, well, when should we treat a fluid as molecules, individual elements, or why don't we treat it as a continuum? Because, as you might be aware, when you open the tap, you don't count molecules to see how long you will have to wait before your glass is filled of water, right? You all look at the glass, say, okay, it's full. But you don't count molecules, or in your, would you pay for water here? Well, yeah, all right. So on your measures of water at home, which obviously I read, I have no idea what I'm saying on water. So anyway, so I guess there is a measure for water at the inlet in your home. It doesn't count molecules, right? Counts something else. So we have to develop some sort of theoretical framework to allow us to go from a molecule perspective to a continuum perspective. Okay? We all live in a continuum perspective because we are, like, let's say, macromolecular, but a fluid is actually contained in molecules. So some of you could ask, like, well, how do we deal with those two things? Okay, so that's what we call the continuum assumption. Okay? And what the continuum assumption says, or postulates, basically say, if I'm looking large enough, I will actually not notice the effect of every single molecule. So I can just look at fluids as a macroscopic entity. What do I mean by that? Imagine we are here in this class, we are all breathing air. This air is considered fluid, right? If I touch the air, which I'm actually doing, I'm deforming the air around. So it means that this air doesn't sustain any shear, so we can consider it fluid. So now imagine this air is actually it's formed of molecules, right? And I'm just going to represent as little knots here. Okay, so now if I take a little volume around one molecule here, well, and then I look at the mass contained, so basically if I do a ratio of my mass over my volume, okay, and I plot here my change in volume. Okay, so now I've done my volume very small. I've set it so small that it only contains one molecule, right? So let's say I'll have here, and the mass here is going to be the mass of these molecules. So I'll have here, let's say, a given value. Okay. Now if I take a larger volume, now I might include a few more molecules, right? So these may go, so I'll have more mass, whatever. Let's say this will keep oscillating, right? And I can keep increasing this, and this will kind of oscillate until it tends to a point that actually flattens out, or that comes to a steady, if you want, flat region here. What that means is that regardless of, I've reached a certain point that regardless of how big I do my volume, the amount of ratio, the ratio between mass and volume that I'm including in that volume remains constant. Okay? So what's important here is the ratio. Okay? So if you want, you can understand these as the proportionality between mass and volume. From a certain point, it doesn't matter how big I keep doing my domain, that the amount of mass that I keep including is about constant. That's what it says. So these would be delta V1 if you want. So it's the minimum volume that I need to consider to actually reach this constant level here. And then if I overpass a certain volume V2, then my density might change again. Okay? Think it this way. If I consider this class as my volume, well, if I'm here, or if I go see where your colleague down there is sitting, or the other colleague down there, or if I'm standing in the middle of the class, the air I'm going to be breathing is about the same. Okay? In the sense that, let's assume the temperature is quite uniform in this class, so regardless of where am I in this class, and I take a volume, a sample volume, the air, the amount of particles that I'm going to be emitting is going to be exactly the same, correct? Do you agree on that? I mean, sometimes I lie, so you should try to make the difference between when I lie. So, but if instead of just limiting our volume of study in this class, and we go just outside the corridor where actually it's much cooler, there's going to be a big difference, right? Because the air, we know that it's denser or lighter depending on the temperature, right? So if I enhance or if I make my volume including also the room outside, this is not going to be any more constant, it's going to start diverging because we have all these effects of temperature and density. So basically, if you see, those of you that like to go ahead, this is what we're going to define or link to our concept of density. Okay? Alright. So, to try to demonstrate that I'm actually not lying for once, let's do like a mental experiment, okay? I think in German, they kind of say like a Gedanken experiment. They just try to play with themselves, like with their mental people. Think it this way, technology was not advanced enough, and you couldn't do experiments, you could still design them mentally, right? You could come with a mental experiment and try to think which could be the different outcomes. That's what we call a mental experiment. Okay? Now you guys are spoiled because technology is pretty advanced, so when we talk about fluids, you can do any sort of thing. So in this mental experiment, let's try to see which could be, for example, the volume that 10 to the 6 molecules, so about 1 million molecules would occupy. Why 1 million molecules? Because, let me ask you, does it make, if I'm giving you $1 million, I wouldn't have it, but let's assume I have it and I give it to you, would $1 million $1 make a big difference to you? No, right? So, it's a decent, large enough number that +1 or +10 doesn't actually make a big difference. Okay? But I mean, it's a randomly chosen number. I would have looked for 10 millions or 10,000,000. Okay? So let's assume we want to have a loop sneak peek of what would be the volume to contain this 10 to the 6 model. Okay, so we all know from an ideal gas that pressure times the volume is equal to the number of volts RT. Okay? So where this is the universal gas constant. A constant that basically has a value of 314 Alright, so now if I rewrite this equation, I just do a little algebra. and then the volume equals to nRT divided by pressure. And now I'll have to just put the number of molecules, substitute all the variables in the standard atmosphere, and I'll get the volume that I'm interested in. Yeah. So here I'll use also the Avogadro's number. Which basically tells me that it's about 6.122 times 1023 mole of this one. Okay, so it tells me about the number of particles on a mole of substance. Okay, so if I substitute all these in here, so for once, and not to be as an example, I'll plot numbers. Sometimes they're useful. So I'll get here 10 to the 6 molecules multiplied by the Avogadro's number Na to the minus 1. Okay? So these will give me the number of moles that 10 to the 6 molecules are. I'll multiply it by these 8.314, and I'll multiply by a standard temperature, that's 293 Kelvin, the standard pressure of 101.3 kilopascals. This gives us about 4 10 to the minus 20 meters. Okay, so this meter cube, because this is the volume. So you can already see this quite a small volume. So if I take my volume as a box, then I'll just say one of the sides is delta L. Okay. So the volume is about delta L cubed. I get that my delta L is approximately 3.4 10 to the minus 4 millimeters. Okay, so it's not even a millimeter here. We're talking about 10 to the minus 4, whatever number, 10 to the minus 4 millimeters. Okay, so I don't know how good your eyesight is, but mine certainly cannot make a difference. Okay, and that was for about 1 million molecules. Right? And we said that we had either 1 million or 1.5 million, not 1.5 million, but let's say 10 more or 10 less, it doesn't actually make much of a difference. Okay? So you can understand at least, hopefully, now you will agree with me and you will be able to tell your grandmother that actually we're good using the continuum assumption and treating fluids as a continuum medium and not as particles. Okay? Is there any question at this point? Right. Whether I am very, very clear or you guys are really sleepy. Hopefully, the first one. Okay. So now I guess I have a few days. Okay, so now we've agreed, so with these we have defined fluid, we have the limits to measure, and we have already defined the concept of density. Now, let's have a look at the very important magnitude. So when we talk about density, now I'll touch your mathematical concepts here. Are we talking about a scalar magnitude or a vector magnitude? Tricky, right? You look worried. Okay, so I'll give you 1 minute. I need you to clarify this with your colleague and tell me the difference, why is what it is and not the other thing. Okay, so now you can chit-chat with him. That's when you have 1 minute to chit-chat with Marcus.
I have no idea.
It's got to be scalar because density just you can multiply by constant, but it's going to be the same. But you can also do but a vector is just a vector is a moving thing, right? And density
I think a vector might just be directionally dependent.
I think it's a scalar because it's just a set thing. Because it's not going to fluctuate. It's not going to move. Yeah, it's not going to move. The density is going to be the density, whether it's in this bottle or whether you're pouring it out over a table. The density of that water is going to be the same. Same with this naked thing. You pour it out, it's going to be the density of that juice is the density in the bottle, and as you pour it out, so it's not going to change. So I think it's a scalar.
All right.
My logic is probably completely inverse.
It makes sense in static systems. In a dynamic system.
Yeah.
So let's do a quick poll. Who thinks it's a vector? Yeah? Who thinks it's a scalar? Okay. We have a majority for a scalar. Okay? So it should be a scalar, or E. The reason why is because it actually is a magnitude that is defined in every single point of the space. Okay? And it doesn't have any direction. Okay? That's what defines a vector and what makes it different from a scalar. A density is just a variable that is defined on every single point in space. So you will have, if we take a Cartesian space x, y, z, it will be defined in every single point there, and it has no direction. It just has magnitude. Okay? All right, excellent. So now, there was saying before, bear with me because now we're going back to some definitions. And I have a couple for you. One is the concept of a specific gravity. This you will use it largely in your homework. Also SG. And it's basically the density of a substance with respect to water. So we define SG is density of a substance with respect to density of water. And we know that the density of water at the standard pressure and so on, temperature, we have about 1,000 kilograms per meter cubed at 4 degrees Celsius, so it's cold temperature. Okay? So this is going to be, you will use these in lots of your homework, because we'll provide, the homework given will provide you the SG, and then we assume that you know the density of water, or you can find these on tables. Okay? So in your documents in Canvas for chapter first, I added like a PDF with a bunch of tables. Use those tables to complete your homeworks, all right? Okay, so another definition is the concept of specific gravity. Sorry? Oh yeah, sorry. Good point. Wait. Yeah. Okay. So this is the weight of the substance per unit volume.
Did he say Unabomber? I heard Unabomber. Okay. I wasn't sure.
Okay, so we have gamma mg by the volume.
Therefore, Unabomber.
Okay. And a value that is partially used is a specific weight of water, is 9.8 kiloliters per milliliter. All right? Excellent. All right. Okay, so here were definitions, and that's the definition of viscosity. Why is viscosity important? Any guesses? They can be wild guesses if you want.
Viscosity affects the quality.
Sure, it affects the velocity speed. So that's a good point. Velocity of the flow. Any other? Interesting. We will see there, we will define two viscosities. There is one that is intrinsic to the fluid, okay? And then there is another one that we divide it by the viscosity and we get another type of viscosity. By the density and we get another type of viscosity. Okay? We'll make that difference, but viscosity per se is a property of the fluid, not of the flow. Okay? So what else? That's how viscosity comes into play. It comes from this interaction on the molecules. That's why I'm saying it's the properties of fluid of the fluid. So it's not the same for oil or for water, right? Sorry? With volume. So it's related to the forces that attract the molecules, sure. But why is it important for us? I mean, I don't care about, or on your daily basis, you don't care so much about the molecules itself, no? But why do we care about it?
It affects boundary friction.
It affects what?
Boundary friction.
Exactly, it affects boundaries and friction. It's the physical world. Everything would be much nicer if we would live in a frictionless wall. But unfortunately, that doesn't exist. At least here. So it has friction. It induces what we know as friction or drag, and it drives losses. Okay? They want to get a pump at home to bring water from A to B. I need to account for the losses that I'm going to have on that pipe. You will see this on a lab. And those losses are due to friction. Okay? And friction is induced by viscosity. Okay? So if you want it the formal way, viscosity is a measure of resistance to deformation by a shear stress. If we take a tube of toothpaste, I'm pretty sure you will all agree with me that it says more viscous than just a little bit of water, right? And And the reason why you're intuitively thinking on that way is because when you want to get some toothpaste, you actually need to press to get the toothpaste to come out, right? So it's the resistance of that fluid, the toothpaste, to actually survive to a certain shear stress. Okay? But now you guys should complain more often, because I've introduced viscosity, and I've introduced a fluid, and I've talked to you about shear stress. But in none of the scenarios I've actually described the shear stress. So you guys are very gentle, because 40 minutes ago, I said, well, how do we define shear stress, right? Because we're using it to define other variables. All right. So, what do we mean by shear? And this is not a simple question. I still even ask it on the qualifying exams for the PhD students. So, any guesses on what's a shear? Wild guesses? Yeah, down there?
Is there a force that acts along the plane?
Very good. But it's a force. So if it was a force, I would measure it with newtons, right? What are we missing on that definition? Per unit area. Yeah. Force per unit area that acts tangentially to the plane. This is the key thing. Why is this crucial? Because now I'm going to ask you, what's pressure? But again, it's a force per unit area, right? So it means if I write it in units, I have newtons meters squared, and I have newtons meters squared. You just said this acts perpendicular to the surface. So keep this in mind, because I'll probably ask it in an exam too. What other difference there exists between shear stress and pressure? Any guesses?
I feel like a box pressure could be a vertical size of a box.
Yeah, so if I do a box, pressure we agreed goes perpendicular. It can be in any of the faces. What else? And we agreed that shear what else? Any guesses? Come on, you're going to be engineers. You will have to come up with ideas, even if you have no freaking idea what's going on. Pressure is a normal force because it's perpendicular, so this is good. What else? Come on. Sorry? With which one?
With shear.
With shear, I can easily get twisting, yeah, but I could also get twisting with pressure, right? Let's say if I had let's say I have this bar that separates two rooms. This has a higher lower pressure, this has a higher pressure, so I have a pressure acting here. I will have a twisting of this bar in this direction. But it's a good point. We're getting close.
Strain is different.
Strain is different, yeah. Well, let me help you out. So the main very important difference between pressure and shear is that pressure is the same as density meaning that it's a scalar. Okay? Keep that in mind. Pressure, you will never see a pressure variable with a arrow or a hat on top of it. Pressure is a scalar. It's defined in every single point of your space, but it doesn't have a direction. Okay? Now you're going to say, oh, you're lying to us because you actually just draw a line in there. Yes, indeed. But I'm not lying. Now you make you guys a little bit of heads up, but what I'm drawing here is not pressure. It's the force exerted by pressure. And that, yes, that's a vector. But the pressure itself is not a vector. Okay? The pressure is just a state of the fluid. Remember, PV and RT. Here there are no vectors, right? It's a state equation. There are no vectors indicating any directionality. While when we write shear stress, the shear stress is a vector in 2 dimensions or a tensor in higher dimension space. Okay? Alright, so just a small detail, but it's very important. Either a tensor or a scalar. We measure with the same variables, they have completely different meanings. Okay? Alright, then just in those 4 minutes that I have before the end of the class, one of your colleagues pointed out the concept that viscosity was related to density. And I said, well, not really, right? Viscosity is something that is intrinsic to the fluid, but it's true that we have another measure that we call kinematic viscosity, and it's symbolized by rho. Kinematic viscosity that we define as the viscosity divided by the density of the fluid. Okay? So here, this is the viscosity which I so up here, viscosity we use, and kinematic viscosity is when we take the regular viscosity and divide it by the density of the fluid. Okay? You guys will be confused. I'm trying to make it easy. So, if I plug the units, okay, so here I'll have kilograms, meters per second, here I'll have kilograms, meter cubed. So I end up with meters squared second. Okay? So this is the kind of question that I'll ask you on the very first problem of your exam, and I don't intend you to remember that by heart, which I've never done, but now you know how to get there. There are just a few things that you need to know, which is basically what are the units of viscosity. Because density, you know how to get there, you know it's certain mass divided by certain volume, so you know mass, kilograms, volume, meter cube. So the rest you can just derive it, okay? But you need to either remember it by heart or know how to get there without memorizing. Either way. Mu is what we define as viscosity. Right? Any other questions? No? Alright, so I'll see you on Friday. Have fun.
Cool. Catch you later. Enjoy the good life. I'm just gonna enjoy the good life once I pay off school.
Really?
The quizzes for the senior seminar thing. Well, no, they have to do them like in class. I don't want to haul around my computer. I don't have to. I do have the book and I've started reading it. Yeah, see, it's like, I'm hoping this will work, but it's a pain in the butt to try to get. I do have the book and I've been reading it, and it's kind of exciting. It's a lot of engineering jargon. To the point where I'm like, how do you know what to do with this book? But it's kind of interesting. It is a lot of engineering jargon, so it definitely takes like kind of like reading a textbook. No, my friend Taylor just said like if it just gets too dry and technical, just skip it. He's like, eh. So I don't think like too in depth there. The quizzes. He read the entire book. Because it's worth writing, apparently.